Okay, in the last video I left you with this set of instructions that you are to use this function, x squared over x squared minus 1, on the interval from -4 to +4 to answer the questions A, B, and C. So in order to locate our critical points, we had to first identify the first derivative and then set that first derivative equal to 0 and find when that first derivative does not exist. So I used the quotient rule in order to find that derivative. Now, on the test last week, you probably would have stopped right here with your solution, but we need to take it a little bit further in this problem because as our derivative is computed, our first derivative is this expression, -2x divided by the quantity of x squared minus 1 squared. We need to find when this derivative equals 0 and when this derivative doesn't exist. Now, to find when a fraction is equal to 0, it's pretty easy. We simply set the numerator equal to 0. So in effect, this derivative will equal 0 when -2x equals 0. And the only time that -2x equals 0 is when x itself is 0. So there's one of our critical points, where it's located when x is equal to 0. We can actually find the coordinate if we go back to the original function. In the event of a derivative not existing, we didn't see that in the last example, but this time it's certainly possible that the derivative doesn't exist because we're dealing with a fraction, and we are not permitted to divide by 0 in a fraction. So in this particular case, the first derivative does not exist when the denominator is equal to 0. And actually that's true for any fraction. If a function is a fraction, that function will equal 0 when the numerator equals 0, and the function does not exist when the denominator equals 0. Now, if we set the denominator equal to 0, x squared minus 1 squared, we do have to be a little bit careful here from an algebraic perspective, because if we were to expand this expression, we would end up with a quartic polynomial that equals 0. And since this is a quartic polynomial, there is a potential for 4 solutions, or there will be 4 solutions, some real, some potentially are not real numbers. So what I elected to do was I factored the interior of this grouping symbol and got x plus 1 times x minus 1. And I recognized, well, the square on the outside just simply means that this pair of factors will be counted twice. We essentially have a multiplicity at both of those positions. So instead of 4 zeros, we find that there are only 2 zeros. And these are not x values that make the equation equal to 0, but they are x values that make the equation not exist, or a solution to it not exist. So when we consider critical points are found at the locations where the derivative is 0 and where the derivative doesn't exist, we know the critical points can be found at the x values -1, 0, and +1. So with all that preliminary work done, I've jumped up here to the right-hand side of this empty space to complete the test. We set up a number line here, and I marked 3 positions on that number line where the critical points existed. So at -1, 0, and +1. And then I started considering numbers in the intervals in between these critical points. So there's a number somewhere to the left of -1 that we would use as a test point, in between -1 and 0, in between 0 and -1, and then to the right of 1. So you can see that the test points that I selected were -2 and +2. That accounted for these outer intervals. And then I chose -1/2 and +1/2 for these inner intervals. And much like the last video, I didn't actually do the math to simplify all of this. I just paid close attention to the signs that would be obtained. When the derivative was evaluated at -2, we ended up with a positive number in the result, because -2 times -2 is positive. In the denominator, I've got -2 squared, which is a positive number. It's relatively large, so that positive number minus 1 is still positive, and a positive value squared is positive. So in essence, we have a positive result divided by another positive result, which will always yield a positive answer. As you get going with more of these examples, you start to recognize that it doesn't really matter what happens on the interior of this grouping symbol in the denominator, because that interior value always gets squared. So every denominator ends up being positive, and we focus only on the numerators from that point on. And at an x value of -1, we generate a positive numerator. At an x value of 2 and 1/2, we generate negative numerators. So when a negative number divides by a positive number, we end up with negative results. And that's why we know that the derivative in this pair of intervals above 0, we have negative derivatives, or a decreasing function. And on the left-hand side, we have positive derivatives, or an increasing function in both cases. Now, because of the derivative test, we know that a local maximum will occur when the derivative switches from positive to negative at a transition point known as a critical point. But over here, since we both retained positive derivatives, there is no maximum or minimum point here or here. Now, as it turns out, the number -1 and +1 not only produces an undefined result for the derivative function, but it also does so in our original function too. If I were to substitute -1 or +1 into the original function, I would get an undefined result. And so that tells me that we're dealing with a non-removable discontinuity. That's a term from our first unit, and a non-removable discontinuity does create asymptotes in our graph. So at -1 and +1, we've got asymptotes. At an x value of 0, we have a relative maximum point. And so I know our derivative is equal to 0, so I know we're at a high point in the graph. And if I consider the shape of this graph, well, the function in this region from -1 to 0 had a positive slope. So if there's a positive slope, then that means this function is increasing on that domain. And if I come from the left-hand side, it too will be an increasing function. And it might race upward towards infinity like this. I have it leveling off at 0 because in the back of my mind I also recognized that, actually I should have that leveling off at 1, because if we're looking at our coefficients here, x squared and x squared have coefficients of 1, and based on end behavior of a rational function, this graph will tend towards 1 as we approach infinity and negative infinity. Now in the next regions of the graph, well, we hit a high point here at 0, and then as we move to the right, we have a decreasing function. So from left to right, it continues to decrease. We are approaching this vertical asymptote. And then we continue to have a negative or decreasing function on the right of an x value of 1. So the graph might be doing something like this. Now, as we studied rational functions back in pre-calculus, there is some more analysis that we can apply in order to sketch this graph or draw it correctly, but this is the general behavior of the function. If we needed a precise graph, we would of course do additional work, but for right now, if we're looking for the characteristics of the graph, I think this does a nice job of presenting that. Though I am thinking to myself here, what if x was 0? That's easy to substitute into the original equation. If x was 0, we'd have 0 squared divided by 0 squared minus 1. Well, that's going to end up equaling 0 as it is. So this middle section, this maximum point, occurs at the coordinate 0, 0. So I can cheat just a little bit with my electronic ink, and I can move that down a little bit further. And now we have what I believe to be is a pretty good representation of this particular function. Now, as far as part C goes in this problem, it says to identify the absolute maximum and minimum values. And if you recall, the absolute minimum and maximum will occur based on our EVT, extreme value theorem. And the extreme value theorem had two checkpoints. We had to determine, is the function continuous? And we also have to verify if the function is closed. Well, the function is closed because we did provide a closed interval on which to focus. It wouldn't be closed if we actually let this graph extend forever towards infinity. I did specify an ending point, so if this is 1, 2, 3, 4, this graph would technically end here, and it would end also at -4, which is right about here. Sorry that this is all running together, but it's definitely a closed interval. There is an ending position to it. But since this function is not continuous, we verified that by double checking this x component and this x component in our original function. Since this function is not continuous, then there's no guarantee to find the absolute maximum or minimum point. If the function was continuous and closed, we would find the function value at each critical point and at the end points. And while we can find the function values at the end points, we cannot find the function values at all critical points. So we can find the function value here and here and here, but we can't find the function value here and here. And as it turns out, there will be no absolute maximum or no absolute minimum on account of these asymptotes. So, no solution for part C. Now, while we've been talking about derivatives, first, second, and third order derivatives in this particular class, one definition that I glossed over due to time is this definition for concavity. The phrase was mentioned a time or two, but we never really applied a formal definition to it, and we really didn't spend much time talking about it. In order to apply what we call the second derivative test, we have to have at least a rudimentary understanding of concavity. Now, concavity is the description that we provide based on the second derivative, and it's analogous to the description that we apply to the first derivative and slope. So the first derivative tells us all about a function's slope, and we decide whether the slope is positive or negative. In this particular graph, you can see that the slope is entirely positive. Every coordinate on this particular graph has a positive slope. The function itself is increasing. Well, except for maybe this point right here. That central point might have a derivative of 0, so it's not increasing nor decreasing. But every other point we would say is increasing. Now, as far as concavity goes, we say that a function is either concave up or concave down, and a lot of times students tend to pick up on this pretty quickly. If you had to guess, this section that I'm highlighting in yellow here, would you say that that is an example of a function whose concavity is up or down? By way of comparison, this section of the function has a different concavity. Would that one be concave up or down? Well, as it turns out, this one here, this section is what we would say is concave down, and therefore the second derivative in this interval is going to be negative. The behavior of the second derivative implies the concavity of this function. And over here we would say the function is concave up, and that's because in this entire interval the second derivative is positive. Now, the way I describe to students this notion of concave up versus concave down is I think of more extreme cases, and I consider the endpoints where it kind of looks like the bends or the twists or the turns in the graph start to change. So I put two little arrow points here, and if you notice, those two arrow points are essentially pointing up, and therefore if the arrows are pointing up, we would say that that section of the graph is concave up. Similarly, over here at this transition point, the graph is still pointing up. At this transition, or at this endpoint, the graph is still pointing up, and so I would argue that this function is concave up in that domain. You'll notice that a positive second derivative in each of these yellow sections does not necessarily correlate to a positive first derivative. In fact, on this section here, our first derivative is negative, even though the second derivative is positive. That's entirely possible. Over here, we've got a first derivative that's also negative, but the second derivative happens to be positive. Now, if I consider the endpoints of this middle section of the graph, say this section is pointing down and this section is pointing down, well, that range happens to be concave down. The endpoints seem to be pointing downward here, and so we would say that our second derivative is negative for that interval. We sort of have the same thing here in this example. We definitely would say that we're dealing with a function whose concave up. Clearly this endpoint is pointing up, but this endpoint of that section not quite pointing upward yet, but compared to one another, these two tails are starting to bend upward, whereas in this other example, these two tails are starting to point downward. That seems to affect or indicate the behavior of this particular curve. And if we were to continue, let's say, an imaginary curve here, we can see that this curve is tending downward, this curve is tending upward, and that might help you recognize this notion of concavity. Concave up in green, concave down in brown or yellow. Now, where concavity comes into play, the second derivative test, is that if we consider our critical points again, C, if we locate a critical point, and personally I like this second derivative test in conjunction with critical points, because if we locate critical points, as we've done in the past, and I'll use a different color to make this stand out, we've got a critical point here, here, and here. That's where our first derivative, of course, is equal to 0. And if the first derivative is 0 and the graph is concave up at that point, then we have found a minimum. So when the second derivative is positive while the first derivative is simultaneously equal to 0, then the second derivative test implies that we have found a minimum. And that happened twice in this particular graph. In the at the other critical point where the derivative was equal to 0, we've got a section of the graph that is concave down. And so if the section of the graph is concave down, or if that second derivative is negative while the first derivative is 0, then we've found ourselves a local maximum. We again won't know if this is the absolute max or absolute min unless we use the extreme value theorem and test endpoints on a closed and continuous interval of the function, but at least we found local minimum and local maximum points based on the first and second derivative, this second derivative test. Now, there are times where the second derivative test is inconclusive, and that occurs when the second derivative is equal to 0. The function might produce a local maximum there or a local minimum at that critical point. We would most likely have to rely on our first derivative test to answer that question. An example of that might be something like this. Let's suppose I've got the graph of x to the 4th power or x to some really large power. Let's say x to the 100th power. Well, the graph of x to the 100th power is essentially a U-shaped graph. It's similar to a parabola, but at this position here, if I start computing the second derivative, if this was equal to u to the 100th power, or x to the 100th power, I should say, the first derivative is equal to 100 x to the 99th power. The second derivative is 9900 x to the 98th power. Well, the second derivative would equal 0 when x itself is equal to 0. So the second derivative in this particular case is equal to 0, but that doesn't tell us anything about concavity. Certainly, if we look at the behavior of the function surrounding that point, we're going to assume that the function is concave up. But in reality, we don't specifically know at this particular point We don't know precisely there because the second derivative is equal to 0. It's not positive or negative. So that's a little nuance with the rule that we'll have to be on the lookout for, or at least have in the back of our mind, in case we see some undesired results or some unusual results from the first and second derivative tests. Now, in a similar sense to first derivatives and critical points, and second derivatives, when we find a second derivative that's equal to 0, that usually identifies what we call an inflection point. Now, we can't actually say that an inflection point occurs everywhere that the second derivative is 0 or where the second derivative doesn't exist, like we would with critical points. Instead, we say that an inflection point occurs when the second derivative changes. So if the function is continuous and the second derivative changes. And so we might say that where it changes signs in order to be a bit more clear. Here's an example where a graph creates a second derivative that's equal to 0. And if we consider the concavity, it's certainly changing at that point. This yellow section represents a portion of the graph that's concave down. This green portion represents a graph that's concave up. And the point at which the concavity changes, when that second derivative sign changes, we have an inflection point. Here's another interesting example. In this case, f double prime, I should say, does not exist. The second derivative doesn't exist because there's a point of a vertical tangent line right here. So the second derivative does not exist, but we do have a section of the graph that's concave down and a section of the graph that is concave up, and that point at which it switches does meet the criteria for an inflection point. We would call this an inflection point even though the second derivative does not exist. So those first two examples are pretty similar to our definition of critical points. We said a critical point occurs when the derivative is 0 and when the derivative does not exist, and that appears to be true for those first two examples. However, in these two examples, here's one that I just mentioned a minute ago, where the second derivative is equal to 0, but we do not consider this an inflection point because the concavity does not change. The concavity is entirely upward for this section of the graph. And I realize I may have misspoken a few minutes ago. I can't recall specifically if I said there was no concavity at this point or if I said that it would be difficult to determine based on that single point. What I really want you to take away from this is that this function is entirely concave up, but if we were just to test a single point, we wouldn't be able to know that. We'd have to look at positions to the left and to the right, and we might consider our first derivative in order to do that. So over here, we've got another second derivative that does not exist because of this cusp of the graph, but the concavity doesn't change either. This section of the graph is concave down. You can kind of see how the whole graph is curving downward. And this section of the graph is also concave down. So we had a second derivative that doesn't exist, but the function is concave down in all points surrounding it. So therefore, this is not considered an inflection point because concavity does not change. So I'd like to challenge you again to complete example 6 on your own. You must sketch a function that satisfies each of the conditions on some interval. You get to decide what interval to sketch this graph on. But in part A, you have to sketch a graph so that the function has a positive first derivative and a positive second derivative. In part B, you have to sketch another function whose first derivative is positive, but the second derivative is simultaneously negative. So on an XY axis, can you come up with a sketch of a graph that meets those criteria? Go ahead and pause the video now and try this on your own. Resume playback in a moment to check your work. Well, here are a couple examples. You'll notice that in both a and b, the first derivatives are always positive because the function is increasing. So these requirements here tell me that the function had to be increasing over the interval. In the first example, however, we were told that the second derivative had to be positive, so this tells me that the function has to be concave up, and I made sure to sketch a graph that was turning upward. In the second example, the second derivative was negative, so I knew the graph had to be concave down. So if we were to answer part C, which of these would we rather have, f or g, as a function that represents the market value of a house that you own? Well, I don't know about you, but I would choose option A. And I like option A because the slopes are getting steeper. So the slope at this point compared to the slope here and so on, the slopes are getting steeper, which means that the value of the home is increasing at a faster and faster rate. Now the value in part B is always positive and it is always increasing. We always have a slightly positive first derivative, so the value is going up. It's just not going up as fast, or it won't continue to increase quite as fast as this example over here. So as far as an investment goes, the market value, I'd much rather have a graph that follows this behavior on the left. Let's finish out this video by considering two examples. On the left, we've got a polynomial function, and on the right, we've got a trigonometric function. And actually, since this trigonometric function is an inverse trig function, maybe we'll hold on to this and talk about it next time we're in class together. So you can make a note that we'll wait on this until next class. You don't have, or you likely don't have the derivative rules associated with this inverse function memorized, so we'll revisit that at another time. So we'll perform the second derivative test in order to find where this function is concave up and down, and also we'll consider a first derivative test at essentially the same time as well, and that'll help us identify maximum and minimum points in addition to just inflection points. So let's see here. To give myself some room, I'm going to jump over to this side and I'm going to start reporting the first derivative. Well, this function should look familiar to you. We've got 12x cubed minus 12x squared minus 12x plus 12. And then immediately we'll compute our second derivative, and that's 36x squared minus 24x minus 12. Now, we would like to know when this second derivative is greater than 0 and when it's less than 0. So to make that easier, we'll just go ahead and find where the function is equal to 0, and then we'll consider points on either side of that to determine whether the derivatives are positive or negative. There again is a common factor of 12 in this expression. So when factored, we're left with 3x squared minus 2x minus 1. We could then factor the remaining trinomial, I hope. And so if I were to guess and check, I would say that 3x times x gives me x squared, 1 times 1 gives me 1, and if I had a negative sign here and a positive sign here, then foiling would give me a negative 3x plus 1x, and that gets me back to the negative 2x. So we've factored, and therefore the second derivative will equal 0 at an x value of negative 1/3 and at positive 1. So if I draw a number line for the second derivative, I would like to mark on that number line negative 1/3 and positive 1. So here's a positive 1, and let's say that this is negative 1/3. And so in order to determine whether the second derivative is positive or negative in the intervals in between, what I would like to do is pick points in between on these intervals. So I might evaluate f double prime at, I don't know, negative 1. I might evaluate f double prime at 0 for this guy in between, and then I could evaluate f double prime at 2 as well. So f double prime at -1, at 0, and at 2. I'll do that, but I'm going to do so off screen. And so after setting up, I realized that I've got a positive number on this factor, a negative number from this factor, and another negative number from this factor. Positive times negative will equal a positive result. Positive factor because 0 plus 1 is positive, and then 0 minus 1 is negative, so that's going to result in a negative second derivative. And then a positive factor times a positive times one more positive will again yield a positive factor. So this range, or this interval of values, will contain a positive second derivative. So based on that analysis, I would say that both -1/3 and 1 are points of inflection because our derivative, our second derivative, is changing. So we've got 2 points of inflection, and if the problem was to ask us only, well, I guess it does ask us to find the inflection points, well, we found them at x equals -1/3 and at x equals 1. And with these x values, we could substitute them into the original equation and find the location in space where the inflection occurs. If we were doing a full analysis on this question, we might end up doing that. Now, just to show how the first and second derivative tests can work together, I'm going to think about this first derivative again. And if you recall, it factored like this: 12 times, we had x minus 1 times x plus 1, but we ended up having 2 of those x minus 1s. So we squared that factor. And the number line associated with it looked something like this. And we had +1 and -1 on that number line. And both of these were labeled critical points. That's where our derivative was equal to 0. And what I'd like to do is I'd like to combine our first derivative test. So this line represents our first derivative. This number line represents our second derivative. Now here again, I go cheating with this electronic ink. I'm going to drag this thing over, and I'm going to align the ones together because those are in the same position essentially on the number line. So I've got 1 over 1. I've got -1/3 and -1 that are slightly staggered a little bit. And I forgot to mention that in our first derivative test, this region was negative. So I had a negative first derivative, then a positive first derivative, and then another positive first derivative. And if we turn our attention to this position here, I'm going to just drop down and look at this critical point and see how it relates to our concavity. Here we've got a position on our graph. This would produce a position in our graph where the first derivative is 0. So where the first derivative is 0 and the second derivative is positive. So if the first derivative is 0 and the second derivative is positive, that means the graph is concaving up. So at a point where the derivative is 0 but the graph is concave up, that produces a minimum point. Now the first derivative test required us to pick 2 points on either side of that and evaluate it in a function. But sometimes it'll be easier just to find where our critical points are and then substitute those critical points into a second derivative to tell whether that critical point is at a point of concavity upward or downward, and thus identifying our maximum or minimum point. For this other critical point, well, if we drop down and compare that critical point to the second derivative, again, we're seeing something that's inconclusive. While the concavity does change and there is an inflection point on this graph, we don't know if there is a maximum point or a minimum point based on the value of the critical point and the inflection point. However, with the first derivative test, we did note that the derivative did not change. So if the derivative did not change on either side, then we know that this is not a maximum nor a minimum. And so as we continue to practice with these more and more, you're going to find us using both a combination of our first and second derivative tests, perhaps with fewer test points and more just analysis at critical and inflection points. And with that, we can determine the behavior and the relationship of the function's graphs. So I know that there were some technical aspects of this particular video. It may be a bit confusing at first, but as we continue to practice with our Math Excel assignments and further notes, this will become a bit more clear, especially as we get into our optimization problems next week. Thanks for watching.